Second is that you have used it a little in the past. The third, that you've tried out GeoStudio's functionality for Python scripting. Or the last one is that you don't have any significant experience with using Python scripting. So please check all of these boxes that apply to you. And we'll give you about 5 more seconds to check off which ones match with your experience with Python. Okay, 2 more seconds. Great. And he's been part of the GeoStudio team for 10 years now, and he is our scripting expert. So thank you, Mark, so much for joining us, and I will pass the mic over to you.
Well, thank you very much, Catherine. Hello, everyone, and welcome to today's Coffee Corner. In addition to basic scripting, we'll also take a look under the hood at how the API reflects the software's internal structure, including its object-oriented design, controller-based access patterns, and discoverable object hierarchies. You'll see how the model view controller structure enables clean separation between data, logic, and presentation, and how object data sources and controllers expose powerful entry points for automation. This understanding will not only help you write better scripts, but also give you insight into how GeoStudio operates internally, making your automation more robust and aligned with the software's core design. So before we dive in, let's take a look at the outline for today's presentation. We'll begin with a brief introduction to the scripting API and its purpose. From there, we'll establish a foundational understanding of the software's internal structure by exploring the model view controller design pattern, which governs how objects interact with the system. Next, we'll examine object controllers, which are the interfaces responsible for managing structured collections of model elements, also known as object data sources, that provide organized access to the underlying model objects. We'll then demonstrate how to discover and query these model objects through the user interface and show how to access the same objects programmatically using the API. We'll then demonstrate how to access model results. And finally, we'll walk through a real-world scripting example that demonstrates how the API can be used for inverse modeling and thus automating model runs, adjusting parameters, and evaluating results against observed data. Let's start by revisiting the definition of an API, introducing the architecture of the GeoStudio scripting API, explaining its key components, and walking through the overall workflow. So an application programming interface, or API, is a set of rules and protocols that allows different software applications to communicate with each other. In simpler terms, an API acts like a bridge between two systems, letting one system ask another to perform tasks or share information in a standardized way. The GeoStudio scripting API is built on a gRPC-based architecture, which uses gRPC, or Google Remote Procedure Call, to enable efficient communication between clients and server or application. By leveraging gRPC, the API enables fast, structured, and language agnostic, this is fundamental, interaction, allowing scripts to be written in language like Python, C++, or C# to seamlessly access and control GeoStudio's internal services. The components of the API are a gRPC stub, or a program on the client side. The stub, which is auto-generated from proto files, acts as the interface for the client to call remote procedure calls as if they were local methods. For example, if the service defines a get method, the stub will expose a get method in the client's programming language. The stub also handles all of the low-level communication details, serialization, network transmission, error handling, and communication management. The API also integrates a gRPC server on the server side that listens for incoming requests from the client. The server, which is part of GeoStudio, hosts the actual implementations of the remote procedures defined in the proto files. Its responsibilities include registering service implementations based on the defined interfaces, handling incoming RPC calls and returning structured responses, managing concurrent questions so it can handle multiple client connections efficiently, and fourthly and finally, supporting different communication patterns, including unary and streaming calls. Together, the stub and the server form the backbone of the gRPC architecture, enabling structured, high-performance communication between external scripts and GeoStudio. The workflow for using the API begins with a script, which is typically written in Python or C++ or C#, as shown on the right-hand side of the slide. So you have two clients in this case. You have a C# client and you have a Python client. Both of these clients run externally to GeoStudio, but are designed to interface with it programmatically. The script enables a connection to GeoStudio using gRPC, enabling efficient communication between the script and the application. Once connected, the script invokes methods on specific object controllers, which serve as structured interface to various components of the model, including geometry, materials, boundary condition, analysis settings, and a number of other settings. GeoStudio then processes the incoming requests and returns structured data, typically in a format that's easy for the script to parse and work with. Finally, the script leverages this data to automate workflows, perform custom analyses, or generate reports, enabling powerful, repeatable, and scalable interactions with GeoStudio models. Now that we've introduced the GeoStudio scripting API and its overall workflow, let's take a closer look at GeoStudio and how it operates. GeoStudio can be conceptualized as a model view controller architecture that's separated into three interconnected but very important components, each with distinct responsibilities. This separation promotes organized code, scalability, and ease of maintenance. First of all, we have the model that serves as the foundation of the application's logic and data management. It defines the structure of the data, including geometry, material properties, boundary condition, analyses, and simulation results, while enforcing business rules and maintaining the application state. Whenever the data is modified, either through user interaction or internal processes, the model automatically notifies the view to ensure the interface reflects the latest changes. The view is responsible for what the user sees and interacts with, basically your computer screen and your mouse. It presents the data from the model in a user-friendly format like charts, forms, or dashboards. Importantly, the view is passive. It doesn't contain any business logic. It simply reflects the current state of the model. The controller is the glue between the user and the system. It listens for user interactions like clicks or form submissions and interprets them. Then it updates the model accordingly and decides which view should be rendered next. In essence, the controller manages the flow of data and the user interaction. This MVC, or model view controller-like architecture, supports both manual workflows through the graphical user interface and automated workflows via scripting and gRPC. That means users can interact with GeoStudio either directly or programmatically, making it highly adaptable to both exploratory and production scale geotechnical analyses. In this latter case, the services which are registered in the server expose methods, RPCs, that are called on object controllers. As you can see on the right-hand side of the screen, we basically replace the user by the scripting API. Remember that the user is on the other side of the API. So the user is writing a script, which is interacting with the API and interacting with the software, and the information is then shared with the script itself. Now that we've explored the model view controller architecture and how it structures the interaction between different parts of the system, let's zoom in on one of its key components, the object controllers. The MVC controller orchestrates application behavior by coordinating multiple object controllers. Each was responsible for managing a specific domain object. These objects controllers encapsulate the logic for creating, modifying, and querying elements such as geometry, materials, and boundary conditions. Stated otherwise, the object controllers act as a gateway to specific object data sources within the model. Now that we've very briefly explored object controllers and their role in managing how model components behave, let's shift our focus to another key component, object data sources. Object data sources are specialized components that offer structured and centralized access to collections of model objects, such as geometry, materials, boundary conditions, and results. These data sources act as intermediaries between the model data and the object controllers. Stated otherwise, the object data sources define how a particular object obtains its data. For example, a boundary condition might have a data source that links it to a time-dependent function, or a material property might reference a predefined data set. Now, to fully leverage the scripting API, it's important to understand not just where data comes from, but how it's organized. This brings us to the structure of model objects themselves. Model objects are the core entities that represent the data and logic within a GeoStudio analysis. These include geometries, analysis configurations, material definitions, boundary conditions, and simulation results. For instance, we have geometry objects, which can be regions or points. We have material objects, which can be the material model or its properties. We also have boundary condition objects, which can be the type or value of the boundary condition. But then again, the result objects, which can be pore water pressures in a groundwater flow analysis, or then again, the slip surface in a slope stability analysis, or a number of other results. Model objects are structured in a hierarchical manner, meaning that they are organized in a nested framework where higher level objects contain or reference lower level components. This hierarchy mirrors the logical structure of a numerical model. For instance, a project contains one or more analyses. Each analysis includes a geometry, analysis settings, materials, boundary conditions, and results, all of which are represented as distinct but interconnected objects. Understanding this hierarchy is essential when working with a scripting API, as it allows you to systematically navigate through the model to access or modify specific components. So now that we've established the foundational concepts, let's transition into the core focus of today's Coffee Corner. We'll begin by exploring how to discover and interact with model objects through the GeoStudio user interface, gaining an understanding of how the software exposes its internal structure. From there, we'll demonstrate how to access and query those same objects programmatically using the GeoStudio scripting API, highlighting the parallels between the UI and the API. Finally, we'll bring everything together with real-world scripting examples that showcase how these capabilities can be applied to automate workflows, enhance model reproducibility, and streamline integration between GeoStudio and other geotechnical tools in practical, meaningful ways. To begin, I'm going to open GeoStudio and examine a simple steady-state groundwater flow analysis. So let me just share my screen here. And there we go. I'm going to move our example over here. So you should see basically an embankment dam in GeoStudio right now. While it's tempting to proceed informally, I recommend following a structured 5-step numerical modeling methodology to ensure consistency and rigor throughout the process of exploring the analysis. So the first step in the numerical modeling methodology consists in defining the geometry and the geology. In this case, it's very simple, straightforward. It's a simplistic embankment dam on an impervious foundation. So that basically covers the first step. The second step consists in defining the physics at play and and thereby the partial differential equations that govern the process, as well as the material properties that define the material behavior. So how do we define the physics? Well, we can either go through the define project, or we could go through the main dialog boxes at the top. So define project, and in this case, we're running a water transfer analysis, and we're using a steady state type analysis, meaning that the terms on the right-hand side of the partial differential equation are set equal to 0. So we're using a specific partial differential equation in this case. If we were to explore the materials, so define materials, in this case, the material is named embankment material. It is a saturated, unsaturated material model with a volumetric water content function, a hydraulic conductivity function, and there is no anisotropy in this case. So we basically covered the second step of the numerical modeling methodology and covered the basics of the physics at play and the material model. Let's move on to the third, which is the boundary conditions. So what's the boundary conditions in this case? So we can either explore the boundary conditions directly through the main menu at the top or through mouse clicking on the geometry. First thing we'll do is we'll explore them through the main menu. So define boundary condition. We have a reservoir level boundary condition on the left-hand side of the embankment dam. And what's this boundary condition? It's a water total head boundary condition named reservoir level, and it's set to a value of 11 meters. We also have a potential seepage face boundary condition on the right-hand side of the embankment dam, which allows water to leave the domain if the pore water pressures are larger than 0. So how is this done? Well, basically, we set the water rate equal to 0, but most importantly, we toggle on a potential seepage face review to allow water to leave. So this is one way of exploring that, but we could also explore it by clicking on the right-hand side mouse button and viewing the line information. So as you can see, we have the information here, and if we toggle into our hierarchical data information, we see the boundary condition on that side, and we could also move over to the other line where we have the boundary condition on the right-hand side. So basically, we've covered the analysis in this case, and we could also go ahead and solve the analysis and then interpret results. So all of what we've looked at can be modified with the scripting API. But how do we identify the components that can be modified with the scripting API? Well, in order to define these things, we have to go into, or ideally, we go into the sketch text dialog box. And what we'll do is we'll insert fields. And this essentially is highlighting the objects within the hierarchical structure of GeoStudio. So the first object that we'll have a look at, following that same structured modeling methodology, is defining the geometry. So what about the geometry? So the first thing we'll have to look at is the name of the geometry. We can insert that, and we essentially get what we call a contextual reference. This is a reference to the name of the geometry. If I were to click it here, we see the name, and it provides the name of that geometry. So let me just clarify by adding some text here. So this is geometries, and this is a contextual reference. Why am I stating that it is contextual? Because it is in the context of a specific analysis. Current analysis, geometry item, name. We could also, let me update that or apply it so that you can see exactly what I've written. And we could also add, for example, a component of our geometry, let's say 0.3. So we could add 0.3, and if I update that, we see the coordinates of 0.3. Well, basically, these are references to the objects that you could later on either modify within the user interface or within the scripting API. So we could use a contextual reference, but we could also use a direct reference. So what's a direct reference in this case? So as we stated previously, we talked about objects. We have a parent object. So what would be the parent object in this case? It would be geometries. And what would be the child object, meaning the object that we want to look at? And the child object in this case would be points 3. And if we were to write that reference, we could basically open the parenthesis, and then we'd write from geometries, we want which geometries are we looking at? We are looking at embankment, dam, and what object do we want? The child object, which is points, and open the points P-O-I-N-T-S. So there's a misprint here. Geometries. There we go. There. So we have the direct reference, which is very similar to going into the dialog boxes, right? We go into defining the geometry. What geometry do we want to define? It's the geometry called embankment dam, and we want to focus on 0.3. So it's no longer related to the analysis, but it's related to the component, which is the geometry itself. So we've essentially shown that we're able to identify objects within the geometry, but let's go through analyses as well. So what are the components of an analysis that we could have a look at? So once again, we're going to have a look at the contextual reference at first, and then we'll have a look at the direct reference. So I'm going to collapse the different hierarchies here, or hierarchical structure of our data. So an analysis would be in the analysis settings, and we can essentially, let's say that we were to select the name of the analysis, and then I'd apply that. So we have the name of the analysis, which is steady state analysis, and we could also select the analysis type, for example. So let's insert that. I inserted it afterward, or before, sorry. Let me just cut that out. There we go. So we have the name and we have the analysis. And let me apply that and zoom out. And if we were to look at it from a direct reference standpoint, so direct reference to this analysis component, so we would have the parent object. So what's the parent object in this case? Well, the parent object is analyses. And what is the child object in this case? The child object is simply analysis type UI. And if we were to write that out, we'd get, so it would be analysis type, and then open the parenthesis, and then from analyses, we want to refer to a specific analysis, which is called 1-steady state analysis. And then what we want is a specific object, or the child object, which is analysis type UI. And I'm not very good at typing on screen like this, so oftentimes I'll make a whole bunch of mistakes, but in this case, it's okay. So we have that direct reference. So this is essentially demonstrating that we can extract or get those references, the objects in the UI, for geometries and analyses. I'm going to move on, and we're also going to have a look at materials, and we're going to have a look at boundary conditions, just to demonstrate how this is done and how we're referencing to these objects, and then we'll move on to the script. So let's have a look at materials, for example. So what can we have a look at materials in a contextual reference? And highlight that like that. So a contextual reference for a material will basically collapse the hierarchy here. And where are materials? Materials are associated with the geometry items. In fact, they're associated with regions. And if we go to region 1, we have the material, and we have the name of the material. And I could insert the name of the material right here and apply that. Zooming out, the material is called embankment material. And we could also have a look, for example, at the hydraulic model associated with this material by inserting the object here. So in this case, if we were to apply that, we're essentially pulling, what type of material is used? Well, we're using a saturated, unsaturated material model. We could also use a direct reference in this case. So what's the direct reference? We have to think about objects. What is the parent object? In this case, we'll have two objects, and I'll explain why we have two objects. So parent object, the first object will be materials, and the second object will be hydraulic, because there can be a number of different properties associated with different physics. We could have hydraulics, we could have thermal, we could have stress strain. So that all of this has to be defined in the direct reference. And we also have the child object, which in this case is seep model. And if we were to write that out as the hydraulic material model, and let's go ahead, open the parenthesis, it would be materials. What materials are we looking at, or from what materials do we want to know the seep model that is applied to that? It's called embankment material, What are the the parent object is also hydraulic. And what's the child object? Seep model. So if I have I have a misprint. So embankment, missing a B here. So embankment material. Apply, and there we go. So we have the direct reference where we're referring to the material, the hydraulic properties of that material, and more specifically, the seep model associated to the hydraulic properties. So let's have a look at one final thing. I'll just zoom in so you can see that. And we'll have a look at boundary conditions. And this will be the final thing that we'll have a look at in the UI, and we'll move on to the scripting API. So BCs. Once again, we have the contextual reference. So what could we look at in BCs? Insert field. Once again, I'll collapse all these things. And just to get an understanding. So where are we applying boundary conditions? We're applying it to geometrical items. In fact, we're applying it to lines. And if I remember correctly, we're applying reservoir level to line 3. So we'll insert the name of that boundary condition, which is reservoir level. And we could also extract the value of, or constant. It's referred to constant, but it's its value, because we could also have applied a function in a function boundary condition. In that case, it would have been a function and not a constant. So inserting that and updating it or applying it, we see that the reservoir level is set to a constant, and that constant is equal to 1. We could also use a direct reference, which is what I recommend because it is not based on the analysis at hand. It's based on our understanding and the way we work with the software in general. And that would be constant and parenthesis. So in this case, we just want to clarify that before we move on. So what is the parent object? Parent object in this case is BCs, and capital BCs. And what is the child object? Child object in this case is value. So going over here, we want BCs. What BCs? BCs. Open the brackets, and then we want, what BC are we referring to? Well, we're referring to BC reservoir level. And what do we want from the BC reservoir level? We want its value. And therefore, if we apply that, once again, I have a misprint. So reservoir level, and apply that, constant 11. So basically, we've shown that we're able to get a whole bunch of objects directly, and these are the references that we're using in order to get them. So when we're going to write a script, we're going to refer to these references, ideally in direct reference format. So I'm going to go over to the script, and what we're going to do is we're going to write a script in order to retrieve the boundary condition value, the last one that we looked at. So the first thing that we're going to do when we write a script is we're basically going to import the different modules that we need. The first module that we're going to import is gRPC, which is the basis of the communication between GeoStudio and the scripting APIs. It's the language or the communication standard that the API uses. We'll also import message to dict from protobuf, which allows us to convert the messages that the API is sending over from GeoStudio to the script and converting those into a dictionary. And finally, we'll import the API itself. Once this done, we'll create a function. So we'll define a function with different arguments. It'll have 2 arguments. The first argument would be the project path. So this will be the path in my file structure to the JSZ file. And the second one would be the analysis name, which we've shown to be 1-steady state analysis. And the function will be returning nothing because we'll be essentially writing to the terminal every time and reporting the values to the terminal. I'm going to add a space up here just to refer to the programming standards. There we go. And what we're going to do is we're going to open the project. In fact, we're going to load the project. First of all, we define the project as none, and then we attempt to load the project. And basically what we're doing here is we're putting it in the try exempt block in order to ensure that if we're unable to load the project, then we're going to report an error message in the terminal. And what's happening here is that the script will be calling out to the API to ask GeoStudio to open the project, and then it will open the project, and that will be it. If it cannot open the project, then we'll receive one of the error message right here. Once this done, what we can do is basically add another try exempt block. And this try exempt block will be retrieving the boundary condition. First thing that we'll do, we'll print to the terminal that we're retrieving the boundary condition, just for clarity. And then we have to define the target object. This is where all what I was talking about in the UI comes into hand. We have to define what object we want to extract. In this case, we're using the contextual reference to that object, which is current analysis, geometry items, line 3, hydraulic boundary, and value. We create a get request. So we're going to basically write what do we want. and then we're going to execute the request. So we're going to send that request over to GeoStudio. GeoStudio is going to send back the answer, and we're going to convert that answer into a dictionary. And that dictionary is going to be called data or data. And once again, good programming practice, we encapsulate all this in a try example block. So if we're unable to retrieve the data, we get an error message in our script. Once this is done, we basically add a print. So we want to print to the terminal the boundary value, and it's simply boundary condition, and we're printing the value of that boundary, of the target object, sorry. Once this is done, what we'll do is we'll finalize our function. We're basically going to close the project. And by doing so, we're going to release the memory, and we're going to basically close the project and allow that memory to be used by other functionality. Once this is done, we're going to write a main block. And basically in this main block, we're going to define the project path, and we're going to define the analysis name. Project path in this case is very long. It's the project path on my computer, which is pointing to that file that we opened previously, which is called embankment dam. As you can see, embankmentdam.jsed, and the analysis name is 1-steady state analysis. And then we're going to basically call out to the function, and that function is going to extract the data. Well, it's going to open the file, and it's going to extract the data using that project path and that analysis name. So I'm going to save the script, and we're going to run it. There we go. So as soon as I run it, it basically gets my Python environment, and it runs the script. As you can see down here, we have written to the terminal that we're retrieving the boundary condition, and that the boundary condition value is 11, exactly as we prescribed or we have shown in the user interface. And this is exactly the value that was applied on the left-hand side of our domain. As previously stated, it's much better modeling practice not to use a contextual reference, but rather to use a direct reference. So how do we write that direct reference? So let me write that out. So direct reference, and I'm going to delete this portion of contextual reference, and we're going to write the direct reference right here. So direct reference is in the BC. C's, we're going to take the BC called reservoir level, and we're going to extract its value. Simply going to destroy that terminal. I'm going to save the analysis, and I'm going to rerun it with a direct reference. And if everything works well, so we're pulling on our environment. This environment was previously created. It includes GSI and a number of other dependencies that we need. And all this, I use MiniForge, but you could use a different type of environment. Forgot to state that the IDE, or the integrated development environment that I'm using right now, is Visual Studio Code. So as you can see, we retrieve the boundary condition, and we retrieve the boundary condition value, which was 11. So in this case, we've shown that we can extract a specific object in the boundary condition, but we could also extract the entire. So let me copy this. And what I'm going to show is that we could extract the entire boundary condition, all the objects that are related to this boundary condition. So its value, its name, its color, if there is a review, the kind. And let's give this a try. The first thing we'll do is we're going to retrieve the full boundary condition, and we're going to state that we're retrieving that full boundary condition when we write to the terminal. I'm going to remove the contextual reference. I could have left it there because it's a comment, but it doesn't really matter. I'm going to remove the value, because what I want now is to extract all of the components associated with that dictionary. So every information that is associated with the boundary condition called reservoir level. The remainder of it remains the same, but in this case, we're not going to print this to file, but we're going to print. So the first thing that we're going to do is that we're going to extract each component or each key of the dictionary. So in the boundary condition, there will be a name, a color, BC kind, a description, a review, and a value. And we're going to refer to the key, which is what I stated, and we're going to associate that with a variable called name, color, BC kind, description, review, and value. And we're then going to print out those values to the terminal. Relatively straightforward, printing out everything that we've essentially associated with the different variables. Once it's done, I'm going to save it, and we're going to run it. I could have commented out the first portion of the code, but I did not. So the code will run through the first portion of the function, which will extract the boundary condition value, which was 11 meters. So as you can see down here, we're retrieving the boundary condition, and the value was 11. And then we're retrieving the full boundary condition, with all of its keys, which includes the name of the boundary condition, the color of the boundary condition, which was RGB or red, green, blue, 128.0255, the boundary condition kind, which in this case is water total head. We have the description, which is none. The review, we had no review on the boundary condition, therefore returned as false, and the value of the boundary condition, which was 11. So basically, we've demonstrated that we've shown how we can identify objects within the user interface, and we've shown how to get those objects within the scripting API. So I'm going to stop sharing my screen, and we're going to go back to the presentation. Okay. Okay, so now that So although we focus exclusively on the get method to retrieve objects during this first portion of the presentation, it's important to highlight that the GeoStudio Scripting API also supports the set method. Whoops, sorry. Something on my screen here. There we go. Which allows users to programmatically assign values or modify model objects, enabling dynamic updates and automation within the modeling workflow. Beyond a deeper understanding of the foundational concepts, the key takeaways here are that we've learned how to explore the structure of GeoStudio model objects and use tools like the sketch text dialog to identify accessible parameters and their locations within the hierarchy. We've demonstrated how to use the get method to extract information from the model, such as geometry, analysis settings, material properties, and boundary conditions. We now understand how to use the get method to extract information from the model, such as geometry, analysis setting, material properties, and boundary conditions. Although we've only done that with the boundary condition, we'd be reproducing that for all the different variables that we've identified, noting that we can extract just about anything or any object that is defined within our analysis. So we now understand how to construct precise references to model elements, which is essential for reliable scripting and automation. Whoops, sorry. Let me go through that again. There was a missing element there. So while not yet covered, the set method opens the door to modifying model parameters directly through code, which is an important capability for sensitivity analyses, parametric studies, and interactive design workflows. So now that we've seen how to access and reference model inputs, let's turn our attention to the outputs, or the results. Model results are presented through a comprehensive set of structured data tables, each designed to display specific outputs from the analysis. These tables provide detailed numerical results for various model components, such as nodal values, element values, Gauss region values, and slip surface data. All of this is organized in a clear and accessible format. This tabular presentation allows users to efficiently review, compare, and extract key performance indicators, making it easier to interpret results, validate model behavior, and support decision-making processes. These tables are not only easy to navigate, but also integrated with IntelliSense support, allowing users to quickly identify and reference available fields and properties. IntelliSense provides real-time suggestions and auto-completions, as we'll later see in the demonstration of the script, making it easier to locate and extract the data you need and reducing the likelihood of syntax errors while writing scripts. This IntelliSense assistance streamlines the process of accessing results programmatically, enhancing both productivity and accuracy in post-processing workflows. So let's go back to Visual Studio Code, edit the name of the function, load the results, and extract the water total head at node 192. So I'm going to once again share my screen. There we go. Should see Visual Studio Code right now. And what we're going to do is we're basically going to, I'm going to delete this so that we have more screen space. We're going to not only use the script to extract objects, but we're going to extract results. So the first thing we're going to do is we're going to rename the function. It will be get objects and results. So and results. And we're also going to rename the function up here and results. And sorry don't want to go up and down, but just for clarity, I'm going to add this and results. So get some model objects and results in the script. And then first thing that we're going to do in the script, we're going to modify the script or the function, not only to load the project, but we also need to load the results. So load project and results. Therefore, we're going to expand this, and all we're going to do is we're going to create a load request. So writing the load request basically is what we're going to send as a message over to GeoStudio in order to extract the or load the results into memory. The second line that we wrote there, project load results, therefore just sends that message over to GeoStudio. So basically now we have the results in memory and we can go ahead and extract them. So we have the try exempt block here for our objects. So we're not going to touch that, but we're going to create a new try exempt block right here. And this will be a try exempt block for extracting results. Once again, using try exempt block in order to report error messages if we're unable to retrieve our results. Very good modeling practice, or in fact, not modeling, but programming practice. Once it's done, we'll essentially write out to screen that we're retrieving the results. I'm going to move this up afterwards when we're finished writing. So retrieve the results. What results do we want to retrieve? We want to retrieve the results that are in a table, and more precisely, let me bring this up here so that you can see it more clearly. So we want to look into the table, in the nodal table. What parameter do we want to extract? Water total head. On step 1, this is a steady state analysis, and therefore we only have one step. And the result ID is 192, meaning this is node 192 in the node table. So it's node 192 that we're trying to extract. The next thing that we'll do, we'll basically create a query request. So we're writing what we want to request and that we're going to send over to GeoStudio through the API. So the request has to include the analysis name, the table on which we want to request that data, the data parameters, the step, and the result ID. Once this is done, we can basically execute the request. So query results request. the response. We're executing it, therefore extracting that from the loaded results. And then what we want to do, is basically set it equal to the value. So what we've extracted or executed, we want to then extract that value and assign it to a variable called values. And finally, what we want to do is basically print that out to screen. So we're going to print out the water total head at node 192. And therefore, that will be the variable, the parameter called value that we're printing out to the terminal. So I'm going to save this. And as you've noted, I've not commented anything out. Therefore, when I run the script, we're going to go into the function. So the main portion will define the path, the file path or the project path. It will define the analysis. We'll then go into the function and we'll go through extracting the objects, extracting the entire object for the boundary condition, and then we're going to extract the result. So let's click on run here. Once again, we're loading our environment and it's running through the script. And we have at the top here, or in the bottom left-hand side, sorry, but at the first portion on the first line, we have the boundary condition value, which is 11. We have all that boundary condition information here. And most importantly, the water total head at node 192 is 9.54. So bear that in mind. I don't want to open and close and go back to the software. I'm going to show you the IntelliSense functionality, and then we'll go back into the software just to demonstrate that this was indeed, or no, I can do that right now. Let me pop up the software. So we know that the water total head is 9.54. So if we close that down, go over to the results view, and if I zoom in, I've essentially identified the object point, the observation point. So if I go into view result information and I click on that point, in this case, we have data type, but the data type is basically the data table. We have the node table, the element node table, the Gauss region table, and the element table. In this case, we want the result from the node table. And we could have a look at the list of variables that are available, but just to highlight those that are most relevant to us right now is the pore pressure and the water total head at node 192 right here is 9.54, which is exactly that extracted through the scripting API. So if I go back to the script right here, and I'm just going to show you the IntelliSense functionality. If we were to, let's say that we're writing out here and we don't know what variable that we want to extract. So I enter E for the different variables that are available or the different results that are available. And then let's say water. And then I could go through the list, scroll down to what I want. But then again, I could complete that water total head. Then I clicked on it too fast, but water T total head. And then I could go, and if I click on the tab, it auto completes that functionality or that variable. I could also enter another variable. Let's say water pressure. Oh, pressure head. Yeah, pressure head. There we go. Going down the list and then clicking on tab, it's water pressure head. I could write that we're going to extract the water pressure head at node 192, save that. And then if we were to run the script, we'd now be extracting the pressure head at node 192. Once again, noting that I did not comment out anything, therefore we're running through the entire portion of the script. But at the bottom right here, we see that the water pressure head at node 192 is 2.64. If we have a look at the software in the node table, we have 2.64 for the water pressure head at that point, or at that node, to be more precise. Okay, so let me stop sharing, and I'll go back to the presentation again. And basically, we'll move on to the next portion. So now that we've covered the fundamentals of accessing and working with model inputs and outputs through the scripting API. Let's bring it all together with a real-world example. So we've developed and continue to build a growing library of real-world scripting examples, all available through our learning management system. These examples are designed to help you apply scripting concepts in practical, meaningful ways across a variety of geotechnical workflows. So let's take a quick look at 3 of these examples. The first example focuses on inverse modeling and specifically the parameter estimation of a multi-step outflow experiment. The second focuses on modeling and visualizing flow paths, while the last example focuses on modeling and visualizing drawdown induced by a dewatering system. The first example is inverse modeling technique to calibrate a numerical model against observed multi-step outflow data, which enables the estimation of volumetric water content and hydraulic conductivity functions. In this case, the modules that we're going to be using in our script are NumPy for array manipulations, Pandas for saving results to CSV, and SciPy, more specifically, the differential evolution algorithm for optimization. This is a global optimization algorithm. First things first, let's focus on the experimental apparatus that we built to essentially extract the results. So we're getting observation data from this experiment. On the left-hand side of this, the screen capture, we have the sample. In the sample, we have 2 tensiometers. These tensiometers are measuring matrix suction within the sample. And at the base, we have a porous plate, and water is being extracted at the base and measured on a electronic balance. So we're basically increasing pore air pressure. As we increase pore air pressure, the suction increases within the sample through axis translation. Water is being extracted through the sample. Matrix suction or suction in the sample is increasing, and we're monitoring that with time. So monitoring matrix suction and the outflow of water. And so let's go ahead and have a look. I'm going to have to share my screen again. So just bear with me. Sharing my screen. Entire screen. There we go. So this is basically our analysis that we've set up. So the analysis that we've set up is a 1D analysis. You have the soil sample in yellow, the position of the tensiometer at the bottom of the soil sample, the porous plate at the bottom underneath the soil sample, and we are basically defining the material properties. In this case, this is important, so define materials, and the material sample is basically defined using a spline data point function that we're going to be populating within the scripting API or within our script. So we have the volumetric water content and we have the hydraulic conductivity function as well. And we'll be populating this as we go along. So basically we've set up our analysis, and what we're going to do is we're going to edit the material properties, edit those spline functions. We're going to run the analysis or solve the analysis. We're going to extract the results. We're going to compare those results to observations. And then we're going to run that in sequence until we essentially minimize the difference between the observations and the modeled results. I'm going to open right now. So the first thing I'm going to have a look at, we are going to have a look at, is the script itself. So you should see the script right now. So the script, basically, at the top of the script, we have a description of what the script does. And then we have the different modules that we're importing. So the description is up here. And then we have the different modules. I'm going to view this in Zen mode so that we're focusing on the code itself. So the first portion is a description. We then have the models that we're importing. we're going to go at the bottom of this script, and what we're doing, basically defining the model input configuration. So we'll have a look at that file as well. It basically defines where the observation data is stored, what parameters we're optimizing, and then we're going to run the parameter estimation routine. So this is a parameter estimation, which is the function. So we're going to go up into the function right here, which is parameter estimation. First thing that the parameter estimation function does is it loads the configuration file. I'm going to move the configuration file into view so that we can have a quick look at what that looks like. So the configuration file includes the project path. So the path to the JSZ file, the analysis name, which is called experiment, the target object, meaning the observations that we're going to use. This is the observed values of outflow and matrix suction within the sample. These are the parameters that we're going to adjust and the range of parameters. So volumetric water content at saturation is not going to change. It's fixed at 0.348. We have the residual volumetric water content, which is provided a range, parameter A, parameter N, hydraulic conductivity at saturation, and L, which is the pore connectivity parameter. We also have constants for inputting the function. As previously stated, the function is a spline function. Therefore, we need a range of values of matrix suction that we're going to generate within the script. And these parameters are essentially going to be useful for defining that range. We then have basically files to output our results, and we have the strategies and the optimization settings that we're going to use for the differential evolution algorithm. So in this case, these are things that you set up for that optimization scheme. We have best one bin, which is the strategy used in differential evolution in this case, population factor, max iteration 50, tolerance between two successive iterations for convergence, seed, and polish. Polish meaning that in this case, the differential evolution is searching the parameter space for the optimal solution. And then we could also run a local optimization algorithm at each point in order to further minimize or find the best solution for our problem. I've moved this out of the way. First, so we basically load that configuration file into memory. We then assign the different configuration components over to different variables in this portion. Then we open the project and prepare the request. Let's remember that in this case, we're going to solve the analysis. We're going to load the results. So we need to create load requests and solve requests for these different components. We're going to load the observations in weights. So we're going to read in the CSV file directly using a utility. And these utilities are available directly in the learning management system. We're going to query the step number. And then we're going to define the parameters or target objects. This is what would be done by essentially identifying through IntelliSense if needed, what were the parameters that you wanted. In this case, it's the cumulative water volume at the bottom of the sample and the water pressure head within the sample at the position of the tensiometer. These are the location of those nodes, right? In the node table, nodes 1 and 8, and the target objects. What are we going to change? So this is what you would have identified through the sketch text functionality in the user interface. You would have identified these functions directly. And then what the script does, it prepares the hydraulic function. We can have a look at that. So this is a function called prepare hydraulic functions. So what does that do? We'll go up here and where is that? Prepare hydraulic functions, basically going through prepare hydraulic functions, and we're setting the minimum, the rate, and the number of points in that function. We're setting up a range of matrix suctions between the min and the max defined by the number of points. And we're assigning values of 0 to volumetric water content and hydraulic conductivity. So we're just creating the array, and then we're going to populate the array later on. So array of suction and values of volumetric water content, and another array for suction and hydraulic conductivity. Going down to where we were before. So prepare the hydraulic functions, and then we start the optimization process. Once again, writing to the terminal that we're starting the parameter optimization process. We have the optimization settings right here with all its arguments. And we have the objective function up here. So one last thing that we're going to have a look at in the script is the objective function, just for clarity, going up here, and the objective function. So this is important. What we're doing is we're going to, first of all, it calls out to the objective function. The objective function wants to run the software, but it needs the hydraulic functions, which are not yet populated in the file. So it's going to create using the list of values that we had before. It's going to create the function. It's going to populate the function in our JSZ file. I'll show you that right afterwards, how it does that. And then it's going to solve the analysis. Once it's solved the analysis, it's going to load the results using the load requests. And it's going to extract those results, and it's going to compute the weighted sum of errors using the difference between the observations and the model results. And it's going to do that iteratively until it minimizes the objective function. Just going back to set hydraulic functions up here. So what we're calling is it knows the parameters, given that the algorithm has provided parameters that are selected within the range of available parameters. And then it goes up in here, and it basically defines the volumetric water content associated with the volumetric water content function, or the hydraulic conductivity associated with the hydraulic conductivity function. And then it populates that over into the JSZ file, which then goes through the different process. So this takes a little while to run, so I'm not going to run it, but I'll go ahead and close this and go back to the presentation. And we're going to have a look at the results. So in this case, we're showing in the picture on the right-hand side of the slide, this is the evolution of the objective function. Remember that the objective function is the difference between the observation and the model simulations squared. And this is as a function of the model runs. So we see that the observation function decreases as the model runs increase. We're getting to the best solution, or the best matching parameters to our model, to our observed results. This is a comparison of the modeled results and the simulated results. On the left-hand side, right over here, we basically have suction, which is measured within the sample, and we see relatively good agreement between the measured suction and the modeled suction, except at longer times over here, around at 40 hours, where basically the physics are not necessarily captured correctly. But in the outflow, we see that we're correctly capturing the outflow that is modeled. So there is very good agreement between the observed outflow and the measured outflow. If we go on and we compare the hydraulic conductivity function, so in this case, we're comparing it to independently measured volumetric water content data. We see that we have very good agreement between the volumetric water content that is estimated using the scripting API, and we also get very good agreement for the hydraulic conductivity. So this is one of the examples that you can access within the learning management system. All that is provided directly there. The other example that we have is groundwater worlds. So we can, in the software, in 2D, follow flow paths, but we cannot do that in 3D. So why not use the functionality available in Python and use Python to draw these flow paths. So these are flow paths in an aquifer with various anisotropy. And you can see that the flow path is swirling within the aquifer, which has different layers of different anisotropy. And we can clearly see that we could capture that. And this is done using 3 Python modules, which are NumPy for array manipulations, SciPy for linear interpolation of model data. So we're basically loading the results for the velocity in the X, the velocity in the Y, and the velocity in the Z direction. And we're interpolating that data onto a mesh, and then we're visualizing that data using MayaV. And the last example that we have is simulating and visualizing drawdown induced by a dewatering system installed in a deep, unconfined sandy aquifer near a river. The system comprises 12 pumps, 12 pumping wells, positioned approximately 5 feet from the crown of the excavation. So once again, this is functionality that is not yet available in the software. So you cannot draw a drawdown map. But you can circumvent this limitation by writing a script that essentially extracts the data for water total head, creates the difference between water total head at a given point in time and at another point in time. And this is the drawdown, and it's projected on a 2D plane. And this is done with 4 different Python modules: NumPy for array manipulations, SciPy for linear interpolation of model data. Once again, we're interpolating on a different grid, and therefore we have to use the interpolation scheme. Scikit for extracting surface elevations, and Matplotlib for data visualization. All of this, once again, available through the learning management system. So thank you for joining. This brings this portion of the presentation to an end, and I'll leave it up to Catherine to give the final statements.
Thank you very much, Mark, for that presentation. We really appreciate you sharing your